Thank you for coming. So it's lunchtime, so you are missing your lunch now to attend this presentation. Thank you all. In the next 3 hours, we will talk about Android things. Android things can be considered as a bridge between the physical world and the cloud. So since we know that most of the aspect of the cloud, of connecting an Android device to the cloud is well known, we will just focus on interaction with physical world. We are Giovanni di Gialluca and Stefano Sanna. We are members of the Android lab of Open Reply, one company of the Reply group. And so we hope to bring you a good introduction of Android things and to give you a way to have fun with it. So we know that Android has been introduced in 2008 with the smartphone. Probably many of you remember the T-Mobile G1, the HTC Dream, the first Android smartphone. Then we had the tablets in 2011. That was a Motorola Zoom. Then we had the Android TV and the Android Wear. Then the Android Auto. And at the end, last year, we had Android Things. So boards are getting smaller, but we are in the same environment. So we can feel at home whatever device we are addressing. In fact, we have same architecture, same IDE, same program languages, same framework, same app life cycle, more or less, and same UI, and same application packaging, same security mechanism, and same passionate community, that is you. So we don't have to learn new paradigms to put our hands on Android things. And as I said, we can feel at home, more or less. There is no UI. At least it is not mandatory to have a user interface in terms of display, keyboards, whatever. And this is part of what will be shown in the rest of our presentation. You will have just one demo with the user interface. The rest will be just interacting, as I said before, with the physical world. So there is, in Android things, there is something in and something out. There is a list. In the green, you see something that you can find on Android things, and on your right, you can see things that are outside the scope of Android things. But the basic rule that you can keep in mind is that anytime there is a need for user interaction, that feature could be missing in Android things. So it has already been mentioned during the keynote. So the permissions are granted by default. And of course, there is no possibility to show a dialogue to get access to type, credential, whatever. So we have to rethink about the user interaction that cannot be performed as usual. And today we have mainly 4 boards we can use for prototyping. I mean prototyping because we use system on modules like Intel Edison, for instance, but to put our hands on it, to work with it, we have to have development kits that are not, let me say, ready for industrial products. So the system of modules must be plugged on a board that will be on your embedded devices, whatever it will be. As you can see, there are different prices different performances in terms of CPU clock, RAM available, storage, display. As you can see, there are two boards, the Edison and the NXP, that have no display, no camera. You have different kind of connectivity possibility, like Bluetooth, Ethernet, Wi-Fi, and USB and some input-output connectors. So based on what is your need, you will have to choose the right board for your prototyping activity. But if you want just to play with Android things, you want to spend some time to learn how it works, we suggest you to consider the Intel Edison and the Raspberry Pi 3. So the Intel Edison is damn small. It's incredibly small. And there is no UI, no Ethernet. So it is, let me say, a very good platform to work thinking about an object that must be connected to the cloud with some intelligence and no UI at all. Raspberry is much more, let me say, friendly for the developers. So we have Ethernet for debugging. We can connect an HDMI screen to see at least the IP address of the device. That could be useful if we want to discover how to connect with the ADB bridge to the board. And we have also the possibility to connect a camera. And last but not least, this is the only board that has the operating system on a micro SD card. It means that you can do your experiment, remove the SD card, put a new one, without breaking what you have already written, and that works. Okay. Main difference from our point of view between Android things and Android. So currently there is no Bluetooth. So Bluetooth is supported by the hardware, but currently the API is not enabled. So of course it will arrive. Bluetooth Low Energy is one of the key technologies for Internet of Things. So we have just to wait, hopefully, for the next developer preview. And so there is on some boards no runtime clock. It means that if you unplug your board, there is no battery that counts the time for you. So this must be to be taken into account. For instance, in a public key infrastructure, if you want to validate these digital certificates, if you are considering, for instance, a Raspberry for a production environment, think about the removable SD card that is not the best for security. And there is no alarm for low battery. So consider that your device is not plugged to the main socket, and it could be powered off suddenly if the battery is not enough energy. There is no GPS on board, even if we have the possibility to write the driver for having location services. And there is no power button, let me say. So once the board is plugged, it boots and runs your code. Okay, this is the theory. Okay, I think it's time for hello world, hello things. I give the microphone to Giovanni.
So, hi all. When you start to study new programming languages or new operating system, you always start with the same example. Obviously, this is a hello world, but we want to be some hardware oriented, so more hardware oriented. So let's build our project. So adding the dependency on our build Gradle, then we have to add a new intent filter on the manifest and the user to to declare that our application will use a user library provided by the operating system. Then we finally could move to our main activity, retrieving the new peripheral manager service instance. Then we could finally open a new GPIO connection and interact with it with this .set value method. And is up running right now. I know that all of you cannot see that, so maybe at the end of this talk you can move near the desk to see them, all of them. Okay. Then let's start with proper theory. Okay, this is there are maybe 3 peripheral types, simple peripheral types. The first one is the GPIO. The GPIO has 2 logical value and 2 electric states, or true or false, and high or low. If you want to change these association, you need to use the set active type passing active high or active low if you want to switch this association. As we said before, you have to get a peripheral manager service instance. Then you can maybe list all the GPIO available on your developer board. Then finally open the connection, use it with the set value command and or get value to read the state of the of that GPIO. Or maybe if you don't want to have a polling process to give the GPIO value, maybe you want to register GPIO callback to be notified when the value of the GPIO will change. So the GPIO callback, basically it has 2 methods, on GPIO error and on GPIO edge. You have to remember that on the GPIO edge you have to read again the value and return true to continue to listening. Then the second peripheral is a little bit more complicated, but this is a way to provide a different signal to our peripheral device. This is PWM, pulse width modulation. It's characterized by the frequency and duty cycle. Maybe you all know about frequency and period. What about duty cycle? Basically, is the time of the value is I on the period, is expressed by percentage. And then we now could use to drive a servo motor, maybe. So starting to list all the PWM devices, open the new connection with the new PWM, and then set the frequency, digital cycle, and finally with the method set enable true, you will start to the signal through the to the PWM pin. And this is a typical value for this specific hardware. The last one, not least, there is the analog signal. For the moment, is supported by Intel Edison Arduino breakout board, but is not still available on Android things. The moderator of the Google Plus community say that is coming soon, this feature, and for the moment we have to use an external analog to digital converter. So there are complex one and simple one. Let's start from let's see for an example of a driver for ADC. This is basically one of them. It has 8 pins out, and just to know how to use them, the first one is used to start communication. The other one are 2-channel analog input signal, the power that we have to provide to this component, and then there is the clock signal, the output, and the channel selection to switch between channel 0 and 1. So as you can see, the output of the component is D0, so will be the only in input, the only in GPIO for our board. Basically, with a simple for loop, we will choose the channel, and then we can read the value, switching the bits by the clock signal. Now let's move to a more complex interface. They are the serial communication. So basically, we have to start to know the name of the serial communication available on our boards. They are basically a list of strings, okay? And then get I2C, get UART, and SPI. So let's start with the I2C. Something about this communication is synchronous, so we suppose that there will be a clock bus, so but it has a fixed clock speed. It's half duplex, so we will have just one bus for data, and it has a master-slave architecture developed by software. And you have to remember that the bound rate is slow, so it's not used for high-speed communication. What about our peripheral device that we want to interact with? We have to know that each I2C device has its own address embedded by the manufacturer, and we have to look for it. Okay, and in specs we have to find also the addresses for all the information is like registers that you will address through the I2C, and the data will be MSB only. So as I said before, there is the clock the clock data, the clock bus, the data bus, and a common ground. As a normal GPIO, we use an manager.open I2C device to open the communication. And what we need to know about the I2C, or what we have to remember about I2C, is that the word of addresses, because when we open an I2C device, we have to pass the bus name and the I2C address, that is that address embedded by the manufacturer. Let's go a little bit low on the communication, because looking for the low level, there is the system management bus. So the system management bus consists on two I2C transactions. The first one provides the slave address and the register address. The slave address is that address provided by the manufacturer, and then the second interaction is driven by the master, if it's a write transaction, or driven by the peripheral if it's a read transaction. So as usual with the with this register, we could read a write register, normal register. So we have just to pass read register and the address. We could read a bunch of addresses, or a single word that is a 2-byte link-to-endian short. Then we could move to UART. This is the second one. It's maybe the simplest one, often used for communicating with boards or even home appliances, and it's usually used for logging. What about the communication? Is just point to point. We don't have different devices connected to the same data bus, and it's asynchronous, so we don't have the clock signal, and it's full duplex, so it has two buses for data for each one bus for each direction, and we have to retrieve previously the specification of our peripheral device, and they are bound rate, parity bit, data size, and stop bit. There are two basic. There are one basic configuration with 3 wires, TX and RX and ground, but you could set a flow control using the RTS and CTS pin, but they are optional. So as an I2C, we have to open the UART connection, set the specification, and then at the end we could set the flow control. Notice that 88 and 1 will be could be the default configuration, and so finally we set the we open connection, we set the configuration, and then at the end we could write and read data, passing buffer and buffer.length. But maybe we don't have a polling communication. You could register a new RT device callback. So now I want to show you a simple example about I2C and URT. This is let's come back to the presentation, because there is just a little problem. Scusa, così? Così? No.
Guarda che è apparso lì. Ecco, sta apparendo.
Ah, ok. Okay. Basically, the data read from the an I2C temperature sensor will flow to the Raspberry Pi here, and it's measuring the temperature inside here. Maybe the temperature is going up, so and this data will flow to the through the UART pin, converted by a TTL converter to USB, and it comes to the to our PC, and is just serial communication terminal. So it was basically this was the example. I want to give you a little trick about the logic level. Maybe you have a developer board with a logic level on 3.3 volts or 5 volts, and you have to switch to the other one. If you are lucky and you have an Intel Edison breakout board, you could move that jumper up to switch to the 3.3 volt logical level, or maybe you have to add an external logical level converter, setting the two values, setting the LV and HV pins. The last serial communication is the SPI. This communication is a full duplex, so it has two bases for data. It's synchronous, so it has a clock to synchronize the communication, and as an I2C, it has a master-slave architecture. But several SPI slave will share the same data bus, and the master could switch between them, setting I, the value of the one slave selection pin, to select that peripheral device. So what about our SPI slaves? Frequency, BPM, BPW, MSB, or LSB, you could switch between them, and clock mode, you could set different type of clock mode. So as I said before, the connection is the master out slave in for the output data, the master in for the input clock and slave selection. Just one word about this slave selection is usually on internet or documentation you usually see SS, but in other things is CS, is client selection. As the others serial communication, we have to list them then we are able to open an SPI device for the connection, set the characteristic of the clock, the frequency, the bit per word, and justification, and then we finally have an half duplex communication, full duplex communication. Then we could make you an example about the SPI. So I want to leave the microphone to Stefano, that is sleeping maybe. I don't know.
Thank you, Giovanni. So what we have shown till now is a way of interacting with single components. So an I2C, temperature sensor, a serial port to connect to GPS, printer, whatever. But if we move from something simple, let me say, a data sampler. So what Giovanni has shown till now is a data sampler, okay, that can get data, convert it, and put in place some actions. When things get harder, usually working with these boards is not enough. So in the real world, you will experience that you need a daughter board that manages all the sensors for you, all the actuators. For instance, the servo that Giovanni described before, managed all the low-level details for the logic board, and then using a serial communication, SPI in this case, your logic board, your Android Things board will communicate with the daughter board that will manage all the low-level stuff. So, okay, we have now the equation of fun. These are the components of fun from our perspective. So we have Android Things, Raspberry Pi, Brick Pi, Lego Mindstorms that most of you probably know. Okay, it's time to have fun. So we have collected all the things that Giovanni described in this. Just a second. This vehicle. Okay. Unfortunately, it's not easy to show it to you. Okay, let's put it in this way. Okay. So you are invited at the end of the talk to come here and show the demos that Giovanni described, and also to play with the vehicle. Is 50 euros to play with the vehicle. Okay. So what is the difference between this and the rest? That we have a daughter board that is, this one, that is responsible for managing the motors, just in terms of signal, low-level signal to interact with the Mindstorm servo, with the button to power it, to start it up, and to the ultrasound sensor to measure distances. And the rest of the logic is on the Raspberry below, and the communication is done with the SPI communication that has been described by Giovanni some seconds ago. These are the main characteristics of this board. So we can control 4 motors, 4 sensors. There is an extra I2C sensor bus. It means that so Lego does not provide any temperature sensor, okay, but I can connect the sensor described by Giovanni to this connector and to have a rover that explores this room, reading the sensor as shown by Giovanni, and sending the data with any API for a cloud service, okay? So as already mentioned, we have an SPI interface to the Raspberry Pi. There is a microcontroller on this board that manages all those cool stuff, and it is uniform. So we will use the same serial protocol for any of the peripherals, and it has also a power management system, so it informs Android things how long will be life with those batteries. That is important. You remember I mentioned there is no alarm about the battery life. Okay, how many of you usually read the release notes? 1, 2, 3. Oh wow, a lot of people. Okay, because so Wi-Fi cannot connect to the internet if at above. And a new camera capture section cannot be. Who cares? With the Internet of Things, we have to care. Input-output, GPIO, BCM4, BCM5, BCM6 are internally pulled up. So they are sending a signal when used as input. That is the default. Okay. Using the Raspberry as is, it doesn't work with the BrickPy module. No way. It means that first of all, we have to access using the API shown by Giovanni to pull down that values. Otherwise, the board does not work. Again, don't forget to read the release notes of your developer preview of Android things. Okay, so we have to know which are the BCM4, BCM5, BCM6, and to put them down. So this is a picture of the connector of the GPIO connector of the Raspberry. This is the very first step. If you don't execute this one, this example will not work at all. Okay, I don't want to waste your time, but just to give you a different point of view, now we are not talking about signals. I don't know anything about edge high, edge falling. Giovanni said 5 volts, 3.3, I don't care. Now I'm working on a high-level binary protocol. And the BrickPy 3 provides something like request with no response. For instance, we can inform the board that there is an ultrasonic sensor connected at port 1, or we can have requests with responses. For instance, give me the position of the motors, give me the distance of the object in front of me. Take into account that in the case of low-level sensors, usually you get tension level, so you measure voltage. You don't get centimeters or inches as an input. In this case, all the conversion from electric level to centimeters is done by the microcontroller that is a slave for the Android things. And the protocol is quite strange because we have to send as much bytes as we expect to receive as a response, even if we will fill different byte arrays. This is a detail to be taken into account. So there is a syntax. I don't want to waste your time. It is better that we spend the last minutes looking plain with the example that we described in theory. So, for instance, to set a sensor type, we have to send a target device number, a message set sensor type, and the type of the sensor. For instance, 1.14.5 is set sensor type NXT touch on port 0. But there is something much more complex if you want to know if the sensor is pressed, because we have to send the header, the target device, the message. There is a padding because we expect the response message that is longer than the actual request. And then we can control if the message is valid, if it is a touch sensor or not, and if the data sample is valid, and if the button is pressed. Look, knowing that the message is valid and the data sample is valid, it is very important, because this stuff will be done by the people that provides you with the hardware. You don't have to care about This component has this tolerance. This component needs this error correction. It will be in charge of the hardware producer. You will have just to care about the logic. And so, just setting the sensor type would be creating a byte array done like this, and to write to the SPI, as shown before. And okay, there is no answer in this case. So we wrote a driver, and this is the syntax of our driver. There is an error. It's brick pi 3, not 4, but we are looking forward for next release. So we have just to open, set sensor type, for instance. On port 4, we have a touch sensor. If it is pressed, start the motors. And then we set a sensor type ultrasonic, and we want to get the distance in centimeters. Then if the distance is below 20, then we will invert the direction of the motors, so the vehicle will turn, okay? And okay, I think it's time for a small demo. This example is very simple, we know, and for instance, it should be improved adding a gyroscope to know the angle of the rotation, because it is not enough to know the position of the motors, because when you have tracks, the angle that is performed by the vehicle depends on the type of the ground. So if it is, I can't find the word for liscio, can't remember. If it is smooth, it will hang for a while. But if on a carpet, it will turn very quickly. May I ask you to write? Sorry, the vehicle has to get money from the people at the bottom of the room. Okay, now the stuff it is not important, the demo itself, but the fact that we have just written these lines of code with Android things, with the library, of course, and okay, and now it's just controlling the ultrasonic. You can put your foot in the front of it, and it will turn. But you may write a rover that explores the environment, searching for something, measuring the CO2, for instance, of radioactivity, whatever, or just taking picture of a large environment. Okay. The fact is that you can use the well-known API that you use on Android. Okay, come here. Okay. So I can't see any 50 euros note in the front. So the rover is not working properly. Okay, and this is what the demo. So we have time for showing you the demo and for the conclusions. Android things brings what we well know on smartphone and tablets. So the power, simplicity, the community, the code, security, to any object. You can think about having the Raspberry of the Edison on your car, on your wash machine, on your medical device. Don't forget that currently medical devices are not connected to the cloud. It could be very important to save information, to know how the patient feels. And yes, this is in our hands. So we don't need to learn new paradigms or to work with ancient languages or frameworks. We can use something very, very cool. And we expect to see powered by Android things in the near future. We will see commercial appliance for our house, for our cars, whatever. Okay, that's all. We are here to show you the demos, to play with your hands, and to answer to your question. Thank you.